All right, ladies and gentlemen, we're taking a look at section 5.6 today, where we're going to look at the last of our convergence tests for series. These are the ratio test and what's called the root test. And in a sense, they're really one and the same test, as you'll see. Now, the ratio test says the following. Let you have a series with these a sub n terms being non-zero terms. And then let this value rho, the Greek letter for r, hence ratio root r, being the limit as n goes to infinity of the absolute value of the ratio of the nth plus 1 term versus the nth term. In other words, take the generating function for your series, write down what the nth plus 1 term would look like, divide it by what the nth term would look like, and take the limit of that ratio. And this value you get for the limit, called rho, well, there's three cases. If rho is between 0 and 1, it can be 0 but can't be 1, then we have absolute convergence. If rho is equal to 1, then we have a test that is inconclusive. And if the value of that limit of the ratio is bigger than 1, then we have divergence. Okay? And really, this is the reason the values of this are called r, and why they are related to the 1 is the fact that what we're doing with this is saying if this value is less than 1, we can make this series be bounded by a geometric series. And you know, for the geometric series, you have convergence when your ratio is less than 1. If the ratio is equal to 1 in this test, we have an inconclusive result. And the geometric series, you know, if its ratio is bigger than 1, has divergence. So this really is the application of the geometric series to a more useful form, is what we're really seeing here. Okay? Now, there is a related test called the root test, which is really the same test in a sense. And it's the same test in the sense that it's the same setup as here. You have a series with non-zero terms. And you form the ratio, or the root, sorry, as rho is the limit as n goes to infinity. Instead of the ratio of 2, it's the nth root of the absolute value of the nth term. Hence it's called the root test. And the same three results. If this ratio value is less than 1, you have absolute convergence. If the ratio value is equal to 1, you have an inconclusive test. You know nothing from the test. And if the ratio is bigger than 1 in limit, you have divergence. Okay. Now, as you go through this section, the author also provides you sort of a summary of the chapter. He has this little section called a problem-solving strategy to choosing a convergence test for a series. Okay, this is a good thing to read through. It tells you when to consider using the P series, when to consider using the geometric series, when to consider alternating series, when to use the ratio or the root test, and when to use the integral test or the divergence test. Okay, so it's a nice little summary to read through, and I would encourage you to do that. As well, he gives you this chart, Table 5.3, where he summarizes all the convergence tests that can be applied. And that's a nice thing to read through. It sort of summarizes for you. Make sure you understand what that table is telling you when you look at Table 5.3. So remember, review Table 5.3 in this section. Okay, it's a very good review. All right, now let's go ahead and take a look at the exercises where we're going to first apply the ratio test to some problems, and then we'll try the root test on some. All right, so let's start with problem number 318, where the prompt says use the ratio to test to determine whether the series converges. State if the ratio test is inconclusive. Okay. So let's see, in 318, the a sub n generating function form is 10 to the n power over n factorial. And so we want to apply this ratio test. That means I want to take the nth plus 1 version of this in limit as n goes to infinity and define this row value. Well, the nth plus 1 version of this means I increase this n by 1 and I increase this n by 1. So I get 10 to the n plus 1, and here I get n plus 1 factorial. And we divide that by the a sub n term, which is simply this. And we need to take that limit. Now, what you get used to very quickly in using the ratio test is that what you're always going to have is the n plus 1 term up top and the nth term in bottom, so why not simply take that bottom and flip it so that you have the n plus 1 term, and then you multiply it by the flip of the nth term. And in fact, you can go to this form immediately. Okay? In other words, you can think of this test this way up here. It's the limit as n goes to infinity, a sub n plus 1 times 1 over a sub n. And just think about flipping that instead of dividing and making a complex fraction that you're then going to have to flip as your next step anyways. Now, the simplifications that we can do here, okay, you can see in particular why the ratio test is useful. It handles factorials and powers both very nicely. And this is how it does it. 10 to the n plus 1 is simply 10 to the n times 10 to the 1. N plus 1 factorial means n plus 1 times n minus 1 and so on. So it's n plus 1 times n. And anytime you want to stop, you just stop and write factorial to get all the rest of the terms. And now look how that cancels nicely with what you have over here. The n factorial cancels with the n factorial. The 10 to the n cancels with the 10 to the n. And you're taking the limit up top of 10 over n plus 1. And of course, as n goes to infinity, that goes to 0. So the row value you found is 0. And the conclusion from our test, if your row value is 0, then you have absolute convergence. And you're done with the test. Okay? All right, let's try problem number 320. In 320, the a sub n is n to the 10th power divided by 2 to the n. So my row is the limit as n goes to infinity of the n plus 1 version of this. So that's n plus 1 to the 10th divided by 2 to the n plus 1. And then I divide by this term, so I simply flip this and multiply. Now, 2 to the n plus 1 is 2 to the n times 2. So you can think of the cancellation this way. The 2 to the n cancels, leaving just a 2. That 2 can be pulled out. And so I'm taking the limit here of n plus 1 to the 10th over n to the 10th. Pass the limit inside the power. And the limit of n plus 1 over n is 1. So you get rho is a half. And again, when your rho is equal to a half, okay, you have absolute convergence. let's take a look at number, what's next? 322. Where the a sub n, or the series, is given to you, but the a sub n is 2 to the 3n times n factorial cubed divided by 3n factorial. Okay? So that means your rho, the limit, as n goes to infinity of this a n plus 1. All these n's have to be increased by 1. Now think about it. When you increase n by 1 here, 3n. When you increase the n by 1, that's 3n plus 3. Same thing here. Okay, so you're getting 2 to the 3n plus 3. This n increases by 1. N plus 1 factorial gets cubed. This 3n increases to 3n plus 3, just like here. And then we have to multiply this by the reciprocal of the a sub n term. So up top, 3n being factorialed, in the bottom, 2 to the 3n times n factorial cubed. Okay? So now, how can we simplify this? And this is where you really get to practice your understanding of powers and factorials and how they're working. Okay? So let's take a look here. 2 to the 3n plus 3. That's 2 to the 3n times 2 cubed. N plus 1 factorial is n plus 1 times n factorial being cubed. 3n plus 3 factorial is 3n plus 3 times 3n plus 2 times 3n plus 1 times 3n, and then you can write factorial there if you want. Over here, 3n factorial, 2 to the 3n, and n factorial cubed. And now let's do our cancellations. 2 to the 3n cancels with 2 to the 3n. This n factorial is being cubed. Here's an n factorial being cubed in the denominator. They cancel. 3n factorial, cancel. So what I'm left with after those nice cancellations is 2 cubed, which is 8, n plus 1 being cubed, and in the bottom, the 3n plus 3 times 3n plus 2 times 3n plus 1. And now we have to take the limit of that. Well, if I simply take the 8 out and think about the powers here, this is n plus 1 cubed, n cubed plus 3n squared plus 3n plus 1 if I expand it out. Now think about the bottom. 3n times 3n times 3n, 27 n cubed. And then you've got 3n times 2 times 3n and so on and so forth. All these other terms which we don't really care about because those are lower powers of n. What we focus on when taking the limit is the highest power of n. N cubed over 27n cubed is going to go to 1 over 27. So you get 8 over 27 as your rho value. Rho equals 8 over 27, which again is a value between 0 and 1, so you have absolute convergence. So you see what's really nice about the ratio test is because it's so easy to take limits by throwing away the lower powered terms and keeping the highest powered terms as n goes to infinity in this limit, it makes it very easy to compute these limits and get your result. Okay? All right. Let's take a look at 324. Where the a sub n that we're working with in 324 is 2n factorial divided by 2n to the nth power. So that means that the rho is the limit as n goes to infinity of this bumped up. So n bumped up is going to be 2 times n plus 1 makes 2n plus 2. And here, same thing. 2n with the change to n plus 1 is 2n plus 2 raised to the n plus 1 power. And then you multiply that by the reciprocal of this. And now to simplify, you simply think about how does the factorial work? Well, when we say 2n plus 2 factorial, we mean 2n plus 2 times 2n plus 1 times 2n, and as long as we go as we want, whenever we want to stop, we can put a factorial. Now in the bottom, 2n plus 2 to the n plus 1, that's 2n plus 2 to the nth power times 2n plus 2 to the 1 power. Now think about any cancellations that you can do. Well, the 2n factorials cancel. That takes care of that. This 2n plus 2 here cancels with this 2n plus 2 here. And so what I'm left with is 2n plus 1 times 2n to the n over 2n plus 2 to the n. So think about what this does in limit. Okay, the plus 2 and the plus 1 are inconsequential as n goes to infinity. And so the limit is infinity, and when the limit is infinity, that means it's bigger than 1, the series diverges. Okay. Let's take a look at 326 next. See if I can fit this on here. Let's see. A sub n is 2n factorial divided by n over e to the 2n power. So that means your rho is the limit as n goes to infinity of all this bumped up by 1. So 2n becomes 2n plus 2, n plus 1 over e to the 2n plus 2. And we flip this, and we get n over e to the 2n, and in the bottom 2n factorial. Of course, we're going to expand that out to do the cancellation with this. We're going to rewrite this as to the 2n power and to the 2 power, and see what we get out of that. So 2n plus 2, 2n plus 1, 2n factorial. That's how we expand this part. Here, n plus 1 over e to the 2n times n plus 1 over e to the 2 power. And the most immediate cancellation is 2n factorials leave. All right. Now, in limit, adding 2, adding 1 doesn't make a difference. Adding 1 doesn't make a difference. So in limit, since n is getting infinitely large, this is like 2n times 2n times an n over e to the 2n. And in the bottom, the adding 1 to the n makes no difference as n gets infinitely large. So that's n over e to the 2n. And over here, n over e to the 2. And another cancellation occurs here. These cancel. And we also have an n squared here and an n squared here. Those are going to cancel. So you got a 2 squared up top. You have a 1 over e squared in the bottom. In other words, you get 4e squared. And 4e squared is bigger than 1. When your ratio is bigger than, or your r is bigger than 1, you have divergence. Okay? All right. Let's see what we can look at next here. How about we try some of the root test problems next? In 328 through 337, the author's prompt is use the root test to determine whether you have convergence. And so in 328, the a sub n that we're given is, sorry, he writes it with a k this time, it doesn't matter. A sub k given is k minus 1 divided by 2k plus 3, all raised to the kth power. And it's cases like this where you see your index raising as a power that makes a good setup for using the root test version of this test. And so the rho is the limit, this time k, instead of n going to infinity, of the kth root of the absolute value of this. And when you take the kth root of the kth power, of course, they simply cancel. So you're left with the limit of k minus 1 over 2k plus 3. K over 2k becomes a half. That's less than 1, so you have absolute convergence. Your r is between 0 and 1. Remember, it's like the geometric series. When the r is between 0 and 1, you have absolute convergence. All right, let's take a look at number 330. In 330, you get a sub n is equal to the natural log of n raised to the 2n power divided by n to the n power. So the rho is equal to the limit as n goes to infinity of the nth root of this expression. Now, how do we do that? Well, 2n, think about how you can rewrite that. And you'll get a very simple result here. This is the natural log of n squared, all to the nth power. And now you've got the top to the nth power and the bottom to the nth power, so you can take the nth root. Alright, so that's the limit we're going to take now. Now, if you let n go to infinity, the top is infinite and the bottom is infinite, which is the setup for applying L'Hopital's rule. So by L'Hopital's rule, you're going to take the derivative of the top, 2 natural log of n times what derivative of what's inside, which is 1 over n, divided by the derivative of the bottom. And so what you get is the limit as n goes to infinity of 2 ln of n over n, which again is infinity over infinity. So again, we apply L'Hopital's rule, which says take the derivative of the top divided by the derivative of the bottom. And so as n goes to infinity, that's 0, and there's your limit. So when rho is 0, we have absolute convergence. All right, let's try 332. In 332, a sub n is n divided by e to the n. So the rho is the limit as n goes to infinity of the nth root of that. The nth root of e to the n is just e. So that's the square root of e that I'm going to pull outside. And so it's the nth root of n that I have to figure out the limit of, right? Well, take that off to the side. think about how you would do that. Well, that's the classic setup for this indeterminate form where we get infinity to the 0 power, where we apply a natural log to help us write this into a form where we can use L'Hopital's rule. So take the natural log of both sides. Pass the natural log inside the limit. Do so that this 1 over n can come down in front by properties of logarithms. And now we're racing the natural log of n against n, just like we did right here. So we know when we apply L'Hopital's rule now to this, we're going to get this to be 0. The natural log of this limit, y, the natural log of y, the value of the limit, is 0. So y is e to the 0, which is 1. This limit, therefore, is 1 over the square root of e times 1. 1 over the square root of e is less than 1. So we have absolute convergence. All right, let's try one more like this, number 334. Where the a sub k is equal to pi to the k over k to the pi. Pi to the k over k to the pi, okay? So our rho is the limit as k goes to infinity of the kth root of this. And of course the kth root of pi to the k, you just get a pi. Take that pi and pull it outside the limit. And what we're left with here is the kth root of 1 over k to the pi, which means, since this is in the denominator, it's k to the negative pi, and then we divide by the k to make the kth root. Okay? All right, so that's what we want to now figure out the limit of. Well, let's take this just like we did the other one and bust it off and say y is the limit as k goes to infinity of k to the negative pi over k, and then apply a natural log again. So we can use that property of the natural logs that the power can come down. Pass the natural log inside of the limit. Take the power down in front now. And as k goes to infinity, the natural log of k over k goes to infinity over infinity. That's a negative, of course, because of the pi. And that's the setup of L'Hopital's rule. So the derivative of the top, well, there's the negative pi times the derivative of natural log of k, which is 1 over k. The derivative of k is 1. As k goes to infinity, this becomes 0. So y is e to the 0, which is 1. The limit here is 1. So over here, this is pi times 1 equals pi, which is bigger than 1. Therefore, this diverges. Okay. Now, let's take a look at problem number 338. Get a little more practice with these cancellations that can arise. In 338, the a sub k is up top, a very simple k factorial. In the bottom, we have this skipping pattern, 1, 3, 5, 7, 9, and so on, up to 2k minus 1. Okay? Now, this is a good setup for the ratio test. So I want my rho to be the limit as k goes to infinity of this with k increased by 1 k increased by 1 here, 2k increased by 1, that would be 2k plus 2 minus 1 is a 2k plus 1. So not only do you have the 2k minus 1, you have a 2k plus 1 in the denominator. And then you flip this. And now we have to simplify. Well, one simplification that's obvious is all of this goes away, just leaving the 2k plus 1. And this k plus 1 factorial, well, that's really k plus 1 times k factorial, isn't it? So those cancel. You can very quickly see the cancellations. And so all I'm left with is k plus 1 over 2k plus 1. And again, when k is going to infinity, that adding the 1 makes no difference. So this is exactly the same as k over 2k, which is a half. Okay, rho equals a half. We have absolute convergence. Okay. All right, similar pattern occurs in number 340. I'll go to a fresh page for that just in case. Never know quite how much room you're going to need when you work one of these problems, do you? 340, a sub k is up to here in the top. The pattern is now 1, 4, 7 up to 3k minus 2. And in the bottom, 3 to the k times k factorial. So I'm going to use again the ratio test. Rho is going to be the limit as k goes to infinity. I have to take this and increase the k by 1. So obviously I'll have 3k minus 2, but what's the next term? Well, when you increase k by 1, this 3k becomes 3k plus 3. Minus a 2 becomes 3k plus 1. Think about the pattern. 1, 4, 7, you're skipping by 3's. From minus 2 to plus 1 is a jump by 3, so that's working. And here, 3 to the k becomes 3 to the k plus 1, and k factorial becomes k plus 1 factorial. Now, take this and flip it. So 3 to the k, k factorial up top, and this in the bottom. And look at the cancellations. All this gets wiped out. 3 to the k cancels, leaving just a 3, so that's 3 to the k times 3 when you have 3 to the k plus 1. And k plus 1 factorial, see how quick and easy you can do this? That's k plus 1 times k factorial. Well, that cancels, meaning you just take away the factorial symbol, and you're left with a k plus 1. So the limit that we have here up top is 3k plus 1, in the bottom a 3 times a k plus 1. And of course the plus 1's don't make a difference. So that's a 3k over a 3k, which is 1. Now, when your limit is 1, when rho is equal to 1, the test is inconclusive. Remember, you're trying to bound this by a geometric series. You have bounded it by a geometric series where rho is 1. I don't know if that means that my series has rho equal to 1 or less than 1. It's inconclusive, is the problem there. Let's take a look at 344. A sub n equals n to the 1 over n minus 1, all to the nth power. And I think this will be the last one we take a look at. Now, looking at this, hopefully you can understand why I want to try the root test. I have a power of n. I'd like to take the nth root and just make that go away. So rho is going to be the limit, as n goes to infinity, of the nth root of this. And the nth root and the power cancel, and so this is the limit that I'm computing. And so the question is, what's the limit of n to the 1 over n, right? I know the limit of 1 is 1, but what's that limit of n to the 1 over n? So off to the side, what the heck would you do here? you'd use the logarithm to help you with this. You pass the log inside the limit. The 1 over n now comes in front. In front, so put that in the denominator. And now when you take the limit of this, we've done this one a couple of times already, right? That's infinity over infinity. So again, by L'Hopital's rule, it's the derivative of the top over the derivative of the bottom, and you get 0. So y is 0. The natural log of y is 0. That means y is e to the 0, 1. This limit right here is 1. And so what you're getting is 1 minus 1, which is 0. And when your rho is 0, you have absolute convergence. Okay? All right, so now that concludes our chapter on convergence tests. And we concluded with the ratio and the root test. In general, you can think of it this way. The ratio test is the most important of all of the convergence tests we have. Okay? When we're moving forward in the next chapter, we're going to make extensive use of the ratio test. Okay? The ratio test is based on the geometric series test. Okay? So the ratio test almost always is what we're going to be using going forward on every problem. On a very rare occasion, you could use the root test, but almost always you're going to use the ratio test. Now, you're going to see how the other tests still get used, but they serve sort of what I consider a secondary purpose in their use. Okay? The primary purpose will indeed be the ratio test. So please make sure you get really good at the ratio test going forward. And as always, if you have any questions or concerns, don't hesitate to contact me. Thank you.